For the last long video I made, this is going to be a lot of things I did different from the first, like, it's going to be a long while. Anyway, as usual, the link to my textbook is in the description for long format videos. Okay, so first thing we're going to go over is, I mean, do we have to go back to this? Because I think last time I was doing this stuff. Yeah, but I think it looks clean now. One way or another, it looks very decent and it doesn't look bad. So I didn't change much of these stuff. I mean, I left it alone. The only thing I changed is pretty much when I get to this partial derivative with gradients and Laplacian operators, Laplace operators. I used index notation to prove some of these ideals, identities here. If you look at this, I used anti-symmetric to get some of these, you know, I was going to do more, but I realized I didn't do a lot. I just realized that now. I should have done more. Oh well. There's also the Hessian matrix that I put up, but it's basically index notation. You'll see why. Anyways, we didn't touch much of Lagrangian. Did I change any of Taylor series? I don't think so. Hmm. Okay, we'll just move to differential calculus. Oh no, we did change a lot of physics. The reason why I changed a lot of physics because physics was going to be first and then differential calculus, but I changed it back again to differential calculus first. Anyways, because I realized that was a mistake. Over here, there's a bunch of cleanup I did. Basically, it's not really much. I just cleaned it up. Um, but you'll be happy to know that it makes sort of sense what I did. Where are the good questions? Oh yeah, here. Oh no, this was already cleaned. Where's the things I cleaned? Ah, here it is. No, that's not it. Springs. I cleaned this section definitely. Yeah, I cleaned it. I added the vector fields, and then cleaned up all the handwritten stuff to typed. As you can see, there's some questions now, and a full-on question like this explaining how to derive all the three cases. I'm thinking of moving this to the differential calculus, and in the in the this section, just showing the final result of that, and I think that would be great. I'm thinking about it. I don't think I will. Um, but yeah, I did that. And I did this one. I'm definitely thinking of moving that into the differential calculus section because that was a little bit painful. And then I also did a moment of inertia. I fixed all this up to type version to make it good and look good to the readers. It actually does look good now. It all makes sense and everything makes sense. Basic pendulum. I'm thinking of doing another question where we have a pendulum with a pendulum, and the same thing with the that'll give you the same thing as in when we did the massive spring thing. It's just a very complicated matrix. Do I want to do the question? Yeah, I will probably one day when I have time. Now, the biggest change, I mean, in my opinion, is I combined linear algebra with differential calculus because I realized it's not much to linear algebra, even though it's like a full quarter worth of class. It's all just memorization in the end of the day because we learn most of it in trig and recal. So basically, it's just memorizing all this stuff, which, yeah, I mean, I don't think it's that impossible for you to do. Then we go to first priority, which then I had to bring up this. I find this is a courtesy of my university. Found this thing. It's for my 20D class. They give you this stuff. Anyways, from that we keep on grabbing more slope field. Anyways, and then we get the general way, the quick way. This is actually a shortcut. For a first order that looks like this, which is any linear ODE basically. So you could do that, but for the sake of showing, I actually showed the steps for most of them. Yeah, and then I showed the first error function here. You'll see why when we actually solve a actual physical problem that actually does show up sometimes. Here's another question. Anyway, the first real question is has a lot of assumptions. This is salt mixture ODE. Yeah, there's a The reason is I made this list a long time ago, so I don't remember why some of them are here. But basically, this is not really physical real life. Most of this is like, well, it needs to be mixed very well and all that other stuff. Yeah, this was made when I was like in taking this class, so I don't remember like half of why this list exists. I don't know why some of these exist. I don't think some of them should, and I'd actually think some of them shouldn't. Like this one doesn't really make sense to me, so I'm just gonna delete it. Oh yeah, why not? It's my. I don't think there is a reason for me to put that in there. You can quote me if I'm wrong, but yeah, I don't think there is. Anyways, over here, after that, we have Newton's law of cooling, which I'm pretty sure these are good. Uh, yeah, and then we have this one question over here that takes that gives you this long equation. But hey, you got a question. We do a simple DCRL circuit, which is pretty cool. It gives you that. We do a simple DCRC circuit. Oh, that was an RL circuit, sorry, which gives you this, which is a similar, very similar ODE structure. Now, the initial condition of the switch could be different, or it could be going outwards, where there's a uh, big voltage initially, and then you swing it open, and now you have to figure out everything. But I didn't do that one because A, that's I didn't do it. B, I didn't do it. C, I didn't do it. That way. All you have to do is calculate the voltage, and then you figure out the reverse. Anyway, it doesn't matter. I didn't do that way. So, anyways, the first order reaction is a classic example of a radioactive decay. And I think in the AP calculus, you actually do this question. So I remember my AP calculus professor teaching me this half-life, basically. Pretty classic example. And you can prove this by going to 50, and that's 100. Oh, wait. Why is this not right? This graph seems wrong. The hell did I do wrong? It should be 50 and half-life. What is going on? Is it 110? Oh yeah, 110. At time 110, 110 it is half-life. So I was right. I This is right graph. It's not wrong. After here, this is a complicated one because I decided to give a question that is classically in um this is a rod basically that's infinite span. So we're doing a semi-infinite solid ODE. So this ODE, you can't solve this one yet because usually, but we have assumptions here that allows us to solve it. Because assumptions, this works. This works because of assumptions. This is not solvable right now, actually, in a general sense, because we need Fourier series and all that shenanigans to actually solve it. But I'm using assumptions to simplify and let us go through over here. That's basically it. Um, yeah. Anyways, again, these are some error functions. You have two error functions here. You just do some system equation logic to get these graphs. These graphs are cool. Just a little bit of MATLAB and you get them. Um, and then you have angular velocity motion, which is another ODE, which we decide, and then here's a question on it, possibly. Yeah. This integration by part section, you can just go to that section. You can see it. Anyways, we have continuous compounding index next, which is deposit withdrawal payment, basically. And if P divided by R is greater than LO, this is actually another AP calculus question. I remember my AP calculus teacher actually teaching me this. So yeah, so there you go. I'm not done with this one actually. I need to solve this ODE to get the final answer. So it's not that hard. It's just e to the negative 0.1 t. So it's like you just move this down over here, 1 divided by 0.1, and then you get that, and then you put this away. So it's gonna be plus c, and the initial condition for that. You get the point. Anyways, that's all you have to do. I'm gonna stop sharing now. Pause.